To set up the next problem, I want to look at the concept of what's known as a voltage divider. So consider two resistors in series. We have the total current that's going to go through this one, then this one. All right. So the same current goes through. So the voltage, there's a voltage drop across this one, there's a voltage drop across this one, and there's a voltage drop across all of them. All right. Voltage divided by resistance is current. So I can just write IT out here. Voltage 1 divided by R1 will be the current. For the combination, voltage 2 divided by these two added up, volt resistors in series. Okay, and I'll note that I can do V3 over R2. All right. Now, but if I want to get this voltage 1, I can get it relative to 2 because voltage 2 divided by R1 plus R2 is the current through here. So if I simply multiply this R1 up front, I get the portion of the voltage across V1. So R1 divided by R1 plus R2 times V2. Naturally, I could get then V3 as simply the current, or I'll just say R2 times V2 divided by R1 plus R2. This would be the current portion of the voltage going through there, or dropped through there. Voltage isn't moving, so that's not the proper way to say it, excuse me. All right, so this is a very useful tool. We're going to use it in the next problem. So we will set that up here, and here's where we are. I want to find EO, that means output voltage is a function of input voltage. So here I have this system. So here's a voltage source. They're all resistors, so I don't have to use impedance here. And I want to figure out what is this relative to that. So we start at the output and kind of work our way across. So here's, let's see, I got a 10 and a 2 ohm resistor. So there's 12 ohms here. So here's EB. The voltage across these two equals the voltage across this one. So here's EB. EO would be EB divided by 12. These 12 ohms would be the current going through here, times these 2 ohms gives me the voltage E0. So I can simplify that down to EB divided by 6. All right. Now I'm going to look at this and go, okay, once I've done that, I have a 6 and a 3 ohm in parallel here, so we'll combine them. And I have that work right here, 1 over 6 plus 1 over 3. So that becomes 2 ohms. All right. And so I can replace that. And that's what I have here. And then I see I have a 4 and a 12 in parallel. So I'll combine them. 1 over 4 plus 1 over 12. That number works out to 3 ohms. Okay. So I can replace them. And I have this. All right, well, here's EA. There's 5 ohms as it drops down to 0, ground. There's the ground, well, put it right there. Okay, so 5 ohms. EA divided by 5 ohms will be the current through here, times these 3 ohms will be the voltage across EB. Okay, so I will note, if I have, here's 1 EO, and EO is EB divided by 6. So if this is EB, 1/6 times 3/5 EA, 3 over 30 EA. So now I have EO relative to EA. Well, then I go over here. So let's see, 2 and a 3 and a 5. 2 and 3 in series, that's 5. So I have 5 ohms and 5 ohms in parallel. That becomes 2.5. So, and here's 3. So I have 2.5 out of the 3 ohms. Resulting in the voltage drop across here. So EI divided by 3 ohms times this 2.5 gives me, and I can rewrite this as 5/6, get rid of the decimal. So EA is 5/6 EI. All right, but here's EA, 3 over 30. So I just combine them. 3 over 30 times 5/6 EI is EO. But I can reduce this down a bit, so I get EO equals EI divided by 12. So just step by step through this, we can reduce those things down quite nicely. And I will be doing one other problem, and then we're going to move to coupling with magnetic fields. See you in a moment.